Today I'm going to talk about symmetries and transition to turbulence in plane Poiseuille flow. And the talk is arranged in 4 parts. The first part is the motivation, and I'll provide a few 1D examples that will convey the crux of the ideas that I'm going to talk about. The second part is symmetries of plane Poiseuille flow. This is a bit technical, but we'll get through it. The third part is numerical results, and finally we'll go to conclusions. Okay, so let's start. How does transition to turbulence occur? It can broadly be divided into 2 scenarios. One is known as the supercritical scenario, where you have some kind of a base flow, and as you increase the control parameter, the base flow undergoes a linear instability, and then as you keep ramping up the control parameter, the flow becomes more and more complicated, and finally it goes to turbulence. This is what happens in classical Taylor-Couette flow, when the flow between 2 concentric cylinders, when the outer cylinder is stationary, inner cylinder is rotating, and this control parameter would be the Reynolds number of the inner cylinder, or the Rayleigh-Bénard convection. But that's not what we are going to talk about today. Today we are going to focus on subcritical scenario, where the base flow, the laminar base flow, represented here by just the x-axis, is linearly stable for the values of control parameter that are in question, and there are finite amplitude solutions, which are nonlinear solutions, which can go to turbulence, and at these values of the control parameter, laminar flow and turbulent flow coexist. This is called the subcritical scenario. The plane, this happens in like wall-bounded shear flows, like plane Couette flow, pipe flow, or plane Poiseuille flow. I'm going to focus on plane Poiseuille flow. The linear instability threshold for plane Couette flow and pipe flow is Reynolds infinity. Like even if you go to infinite Reynolds numbers, it's linearly stable. But you do see turbulence around Reynolds 2300 in pipe, for example. And in plane Poiseuille flow, there is a linear instability. It happens at Reynolds number of 5772. You get Tolman twisting waves through a half bifurcation, but we are going to focus on Reynolds numbers that are way below that threshold, around 2000. Okay? So we will be in the subcritical regime where linear basic flow, laminar flow is linearly stable. Okay. So when these laminar flows and turbulent flows coexist at these Reynolds numbers, this dynamical systems point of view of turbulence is useful. And in this case, you can imagine, you have a fluid flow and you can take a snapshot. You can, if you have all periodic boundary conditions, you decompose it into Fourier modes, and you represent the coefficients of you represent one state of this flow by one point in the space of coefficients of these Fourier modes. So this is like an infinite dimensional space, and one point represents the entire state of the system. Okay. So in this state, dynamical systems point of view of turbulence, the laminar flow is at the origin. You can set your origin so that laminar flow is at 0, and that is an equilibrium point and stable equilibrium point. And you also have these finite amplitude nonlinear solutions that they come in varieties. They can be equilibria, relative equilibria, which are like travel waves, periodic orbits or relative periodic orbits, which are closed curves in this infinite dimensional state space. And they have many stable directions, but a few unstable directions. And you start with an initial condition. That initial condition is influenced by dynamics, the invariant solution that is nearby. And then the red trajectory is following this periodic orbit for some time. Then it gets sucked into the stable manifold of the invariant solution, and then it gets thrown out from the unstable in the unstable direction, and then it gets sucked into some other stable manifold. And you can imagine turbulence as a chaotic walk in this infinite dimensional state space. Okay, and this is what we also observe in experiments and numerics, where you have, when you have an initial condition, you can, when it's nearby a certain invariant solution, it starts mimicking the dynamics, and then it gets thrown into some other chaotic regime, and then it again gives rise to some spatio-temporal pattern. Okay, so this is why we are interested in calculating these invariant solutions, which form the skeleton of turbulence. And these invariant solutions often have symmetries, and that's why we are interested in the symmetries of the problem, so that we can actually zoom onto these, get to these finite amplitude solutions. Okay, but before we go to the full Navier-Stokes things, full Navier-Stokes equations, I will motivate this by a 1D Burgers equation, and I will, show you the notion of equivariance and the impacts of that. So start with the Burgers equation, ut equal to minus u ux. In the dynamical systems parlance, the dynamics f of u are minus u ux. And consider two transformations, gamma e for gamma even and gamma o for gamma odd, which takes g of x, gamma e takes g of x to g of minus x, and gamma o takes g of x to minus g of minus x. I can show that the dynamics commute with the gamma o operator, but don't commute with the gamma e transformation. So I was explaining the notion of equivariance for the Burgers equation, and I was saying that I have two transformations here, gamma e for gamma even and gamma o for gamma odd, and I can show that the gamma o transformation commutes with dynamics, but gamma e does not. And we say that gamma o, the Burgers equation is equivariant under gamma. The consequence of this symmetry can be seen in these, in the following figures. If you start with an initial condition which is even and evolve it in time, it loses its evenness. But if you start with an initial condition that is odd, it stays odd for all times. This is going to be useful for Navier-Stokes equations, because when we are looking for all these invariant solutions for plane Poiseuille flow, traveling waves, when you impose a certain symmetry, let's say I impose a symmetry in the spanwise direction, it's going to pin that traveling wave in the spanwise direction. So I don't even have to look for a wave traveling in the spanwise direction when I'm solving the Newton solver. Okay, so knowledge of symmetries can help you understand what kind of dynamics is going on. The second thing that is important is equivalence under coordinate transformations. And what this really is trying to say is that sin x and cosine x are essentially have this, they have the same physics. It's just that it's shifted by the coordinates are different. Okay, so if something like this happens, we will talk about the conjugacies. So sigma x and sigma x tau x here we will say that they are conjugate under quarter box shift transform conjugation. Okay, I'm not going to go into this right now because of time, but if you have doubts, we can talk later. Okay, so let's get to the plane Poiseuille flow. The geometry and schematic is represented here. X is the streamwise direction, Y is the wall normal direction, and Z is the spanwise direction. And sorry, but that's the convention that plane Poiseuille flow literature uses, so I'm going to stick with that. And in the dimensionless terms, the laminar basic flow is just the parabolic flow 1 minus y squared in the x direction, and 0 and 0 in the y and z direction. Governing equations are Navier-Stokes equation, incompressible, and the Reynolds number is defined as follows with respect to the centerline laminar velocity and half channel. Okay. The plane Poiseuille flow is equivariant. The Navier-Stokes equations are equivariant under these following transformations. Okay. Sigma y, sigma z, and tau ab. So sigma y is a reflection in the y coordinate, which was the wall normal coordinate, remember. Sigma z is a reflection in the span-wise coordinate, z, and tau ab are infinitesimal translations in the x and z directions. Okay. And the rules of the game are as follows. So you have sigma y, you have a reflection, you reflect something twice, you get to identity. So sigma y squared and sigma z squared is one identity. Sigma y and sigma z commute. It doesn't matter which reflection you do first, you end up with the same state in the end. Sigma y and translations also commute because they are about different axes. Sigma z and translations have a peculiar thing. When you flip the order of operations, you gain a minus sign on B. Okay. And for the rest of the talk, I'm going to use capital Lx and capital Lz as periodic lengths. Okay. Okay, so we're not going to focus on the entire group that is generated by sigma y, sigma z, and tau ab, but we are only going to talk about a specific subgroup of this generated by sigma y, sigma z, and half box shifts in the x and z directions. Why half box shifts? Because when you consider reflections and translations together, half box shifts arise naturally. Here is an example. Consider on an infinite domain. Okay? We have not specialized yet to periodic boundary conditions. So we have infinite domain in x and z, and we have a velocity field u which is invariant under gamma, which is tau a comma 0, which is translation in x by a, sigma y. By invariant, I mean gamma u is u. If I apply this gamma again to the to gamma u equal to u equation and use the multiplication rules, I end up with tau 2a comma 0 u equal to u. What that means is this is implying a periodicity of capital Lx equal to. And now if I specialize from an infinite domain to a periodic box of length 2a, the original symmetry gamma a comma 0 will look like tau x sigma y, okay? Where tau x is the half box shift in the x direction. Okay, so that's the reason when you consider reflections and translations together, half box shifts arise naturally. So we are not going to worry about all the infinitesimal translations. We are only going to be focusing on half box shifts. So we consider this smaller group, which we denote by GH, H for half box, which is generated by sigma y, sigma z, tau x, and tau z. Now remember, by group I mean these and then all the combinations of these symmetries. And now this is, all of them are order 2 elements in the sense that we talked about sigma y squared and sigma z squared being identity. But now tau x squared and tau z squared are also identity because they are half box shifts and we have periodic boundary conditions. So if we do a half box shift twice because of periodic boundary conditions, you get to the same thing. And in this specific case, this is an abelian group in the sense that it doesn't matter which symmetry operation you do first, even in the case of sigma z and tau z, because you remember that there was a minus b sign, there was a minus b when you had a sigma z, but when we are considering only half box shifts, half box shift in the positive direction or in the negative direction are the same thing. So in this GH, it doesn't matter in which order you do the operations. Okay, so what we are interested in is to enumerate all the subgroups of this and then try to understand, which of them are connected to each other through coordinate transformations. We wrote a code in Julia for this because there are too many subgroups, and I'm going to just list them here for completion. You don't have to worry about them right now. But if you are interested, you can talk to me later and we'll go in detail over these calculations. So there are 13 order 2 subgroups of GH, which on a minimal periodic box. But we can only get away with considering 9 of them because 4 of them are equivalent to some other subgroup through a quarter box shift conjugation that I had shown earlier for the 1D example. Okay. There are 22 non-trivial subgroups which we classified into 12 equivalence classes. And then for order 8, we have 4 subgroups and 2 equivalence classes. The numerical results, we performed all the computations on open source code, channel flow 2.0, and finite amplitude traveling wave solutions are found in subcritical regime at Reynolds 2000. And the computational box was 2 pi cross 2 cross pi in the dimensionless length scale, in the dimensionless units. And then NX, NY, and NZ were 48, 49. Here is an interesting computational effect of imposing symmetries. When you impose symmetries, if you know which subspace you are working in, which solution you are looking for, and you impose symmetries accordingly, then you can get order 2 to the power n speed up in your Newton solvers. And this too is connected to the fact that all the generators that we had are order 2. Okay. Here are a few traveling waves with sigma y and sigma z symmetries. I'm showing the x averaged, streamwise averaged YZ cross section. Y is the wall normal coordinate, Z is the spanwise direction. You can see that Z is the, you can see the sigma Z symmetry there. And we also continued them in the Reynolds number using numerical continuation. And we saw that TW9 and TW10, which are labeled accordingly because we have found a few more traveling waves in different symmetry subspaces, are connected to each other through a symmetry breaking bifurcation at Reynolds 1272. Okay. So I will conclude quickly. The conclusion is that if you have symmetries and if you know something about the symmetries of the flow, use them. Yeah. It can, it's not just, they're not just dynamically important, but, they can save computational cost. And we have done a lot more analysis and we have a lot more array of solutions to, and we also analyze the dynamical importance in a paper, which will be uploaded soon. And finally, I will end on a lighter note. You know that Plato wrote about his PhD advisor's allegory of the cave. Socrates' allegory of the cave. So my PhD advisor, John Gibson, also has an allegory of the cave, which is that, transition to turbulence, you're in like a dark cave, but if you know about these symmetries and invariant subspaces, you realize that, okay, wait a minute, it's not that. And then you realize that, okay, there are sub-caves here. And okay, not all those sub-caves are unique. Some of them lead to the same room. So, the doors look different. It's just that they lead to the same room. And, when you're taking the next step, according to guided by symmetries, you are at least sure that the floor beneath you will not slide. Okay. So here are some references, and thank you. If you have questions, you can ask.
Thank you very much, Pratik. Other questions? Maybe students first? And maybe from the whole audience?
Hello.
Hi.
So presumably you can do something similar for the pipe case, right?
Yes.
But then in the pipe case, you wouldn't necessarily have discrete symmetries anymore if you take the azimuthal symmetry be continuous. So how would that, I guess, how would the similar procedure work in that case?
You can still take like a discrete symmetry because it will still be a subgroup, and then you can try to look for solutions. And in fact, many of the invariant solutions that are found in pipe flow have that discrete symmetry in the azimuthal direction. So if you know about that, then you can still do something like this.
Sorry, did you say those are discrete symmetries?
No, I'm saying that the solutions that have been found, invariant solutions like the finite amplitude solutions that have been found for pipe flow, also have more often than not discrete symmetries in the azimuthal direction. So you can you can piece up your entire space into different symmetry invariant subspaces made up of discrete symmetries, and then look for solutions in them. But if you have to worry about the continuous symmetries, then you have to do something else.
If you have to start dealing with Lie groups.
It's not trivial.
Are there further questions?
I have a question. Actually, I wanted to ask you the flows that you showed and the subgroups that you showed. Could you say something about where in the Might Aghor we can find, for example, in the ocean or atmosphere, if you can find some regimes or flows?
Not exactly these subgroups, but I have seen a paper by Roman Grigoriev. They have applied these kinds of ideas to 2D turbulence, which is more relevant for. So you can do similar things for 2D turbulence as well.
Okay, thank you.
Okay, Pratik, then maybe a more general question at the end. You showed at the end Platon's cave. Where are we at the moment? In which level?
I don't know. I mean, we are probably at the second level, maybe. I don't know, first level, second level, I would say.
Okay.
But there is much to be done here.
Definitely. Okay, thank you very much, Pratik. Let's thank him once again.